Let's welcome Shiang-Yu's talk.
Okay. It's very nice to have the opportunity to give you the summary of the status of TAOS II, which we expect to start very soon. And I will give an overview and then give you the current status of the survey. And by the end of the talk, I also have a small advertisement of our science workshop, which will happen in May this year. So let me get started. So, as we know, the Trans-Neptunian objects are the small objects beyond the orbit of Neptune. So with the direct survey, right now it's probably a few thousands of the TNOs that have been discovered, and based on their orbit, you can classify them relatively in 5 different categories. So, is there a pointer? No, this one. No power. All right, that's fine. So we can see here. Here is we call the classical TNOs, which has almost circular orbits. The eccentricity is very small, and also the inclination is also very small, meaning they orbit mostly on the ecliptic plane. And then you have the resonant object, meaning they have shear similar orbits as Neptune. So their period of their orbits are the integer ratios with the period of Neptune. So their orbit is closely tied to the orbit of Neptune. And then you have the red spots, which shows a more chaotic distribution in this plot. But basically, they are the object which you can see they all lie above this line, showing that they have been scattered by the giant planet, mostly Neptune, during the evolution of the solar system. So that's why they typically have a higher eccentricity. And then there are some we call a detached object, meaning that they are sort of further away, have a higher perihelion. So they does not have a strong correlation compared with the other 2 subgroups that I mentioned.
Detached means it can be retrograde?
Well, some of them are retrograde, not necessarily the detached.
But the resonance doesn't happen with retrograde.
I think there was some that was also retrograde for the resonance. Very few, yeah. Okay, so based on this structure, there's been a model that proposed to explain why we saw such a distribution. So this is called the Nice model, proposed by Morbidelli and Howard Davidson. It was proposed in Nice, so that's why I call it Nice model, not Nice model. Nice. That is definitely a nice model to explain what we saw. So basically, what happened was that there were period time has a significant migration of the large giant planets, which sort of disturb the small objects on the ecliptic plane, so that the scattered small object, they either were injected inside the solar system or to the outside of the TNOs that we see. So combining with the original object here, there are clear, distinct of the hot and cold population. Not only we can see from their orbit, but also we can see the different properties from their surfaces. But so far, because these objects are very far away, and then they don't emit light, so our observation has been limited by the reflected sunlight from these objects. So if you use the best telescope in the world now, say the James Webb telescope, you probably can detect objects around 20 kilometers. So anything smaller than 20 kilometers in size, you will not be able to detect it. So the size distribution of the TNOs shown in this plot, they have very nice measurement for big objects, roughly speaking from 600 kilometers in diameter, roughly go down to around 20 kilometers. So as the object becomes smaller, since you can only use a space telescope to do it, so they are like pencil beam measurements here and there. So the error bar is getting larger and larger. And the other way of measuring the size distribution, thanks for the New Horizons mission, people use craters on Pluto, Charon, and Erectus to measure the number of craters and try to estimate the number of small TNOs, because these craters are meant to generated by the impact from the object nearby. But unfortunately, if you compare the measurement from the direct measurement in the craters, they are quite big discrepancy, meaning that if you compare the 20 kilometer object numbers with the direct observation number, there's a big discrepancy, and also the slope that you see is quite different. So in order to, and why this
so
is...
Just to make sure I understand your sentence, you're saying the craters, the results meaning the craters show a smaller number density of smaller objects,
Right.
but your crater density is higher than that line. How am I supposed to read that? So the black line labeled, no, so yeah, what am I reading?
So these are the actual number of the craters that they saw. So this is crater of the Chirons, and this is from this Erectus. This is a very tiny, small TNOs. So even they choose a different crater distribution. They show a different size distribution.
And what does 4 gigayears have to do with this?
I think this is probably some modeling of how the surface was reformed. As we know that on top of Pluto and Chiron, there were volcanic activities. So the impacts, the craters will be resurfaced. So depending on how frequent they resurface, if it's older, then you see more craters, and if it's much newer, then or the frequency is higher, then you will not see that many.
And then what does it mean by empirical saturation?
Empirical saturation, this is probably, I don't remember exactly, but this is probably due to how they can do this. When density is high enough, you can not really calculate.
But again, I couldn't tell from your bullet says the results are much smaller number density of small objects than direct imaging, you're saying, right? But
Right.
How do I see that from that one?
Yeah, sorry, there was no direct comparison, but what I remember is a factor of at least 100 difference if you compare the number density here and here.
So if you made that plot to the right-hand side, it would be
It would be like, yeah. Yeah, so why are we interested about the size distribution of small TNOs? As in many is that we were curious about the process of correlation and then erosion collision process during the formation of a solar system. As you can see, during the process, a small object can break a larger object, and then there will be a cascade process, which depends on the strength, material strength, and also the relative velocity and how the object was distributed and how their orbits were distributed. So there have been many different models. Some of them include more detailed orbit numbers. Some they care more about different impact velocities to try to model what is possible size distribution, especially on the smaller ones. So in all these figures, you can see the green triangles. These are the measurements for large TNOs with a ground-based telescope, and the three solid dots, blue dots, these are the measurement done by the Hubble Space Telescope. So this means the triangular sign are coming from a larger survey covering large area, while the blue dots are pencil beam measurement because you cannot use HSC, Hubble Space Telescope, to do a large survey. But in any case, you can see a big discrepancy of the size distribution in the smaller, for the smaller TNOs. Roughly speaking, there's a range about 10 to the 5 difference, depending on what I mentioned, the collision process, the material strength, and then the impact velocity.
How do they derive this extended to smaller size?
So they assume certain, the smaller object is generally through the collision of bigger ones. Oh. And then you assume different parameters and how they hit, what are the orbit. So there are many parameters. That's why there are so many papers. It's hard to have one paper that consider all the factors, and then
And then this panel is from somebody's paper?
Yeah, these are all from paper.
You've got 6 panels.
Yeah.
And you have 6 authors.
Right.
But the person who made these 6 panels is a 7th author?
No, this is from our proposal. So we combine. Yeah, we combine. Yeah.
But which one is fit better to the less line in the crater size? The size.
Well, the crater is much less, so it's
much less.
Yeah.
The lower right is from the crater.
Yeah, this is from the crater. Yeah.
Okay.
You try to fit the crater. That's why it become flat. You see, so that means the smaller one are actually not increasing.
Yeah, but I thought you said the crater is a factor of 100 below the measurement. So shouldn't that black line be a factor of 100 lower?
Well, if you compare this, yes.
No, to your measurement. No, earlier you said that the crater measurements are 100 times lower in the mass of 20 kilometers where they overlap. Meaning, I would have said that to mean your black line on the lower right should be a factor of 100 lower than your.
Well, I think they try to, because the bigger one is probably much less, the crater with a bigger size. So they actually have small numbers here. So yeah, I forgot how they manipulate this part. Yeah.
Why this plot important?
Why?
Yeah.
As I mentioned, you try to understand in the early days how the planets were formed, how our solar system was formed.
Yeah.
And the material that compose determines, the collision process and how much small object you can get.
Okay. All right.
Yeah. So as I mentioned, because we cannot detect the small object anyway, so That's why we have been using the blind occultation survey to detect the small and faint objects. So for TAOS II, our goal is to detect anything larger than 0.2 kilometer at the 40 AU region. So this is a plot showing what the TAOS II is able to detect. Here are several lines. First of all, the black dots are the known TNOs that has been detected, which has a limit around 20 kilometers, as I mentioned. As far as they get further away, there's a limiting magnitude of settings in R band. So this means the current limitation of what you can reach for the direct detection. But with the occultation survey, basically you are limited by the diffraction process, the diffraction pattern generated by the occultation. So you are limited by the Fresnel scale, as well as the angular size of the background star. So here you can see the black line, black curve is the limitation of a TAOS II sensitivity. So roughly speaking, at 40 AU we can detect about 0.2 kilometers, and at 100 AU you can detect, roughly speaking, 0.4, 0.5 kilometer size. So because this is a blind survey, so we cannot actually determine the orbit. You see it and then it's gone. So we basically can measure the size distribution, and then probably you can measure the orbit inclination distribution if we can get enough events at different fields that we survey.
Why does size depend on distance?
Pardon?
Why does your TAOS II size sensitivity depend on the distance of your object?
Because when you get further away, the angular size of your object becomes smaller. And this occulting process is a process of what's bigger. If a background star is bigger or your object is bigger. When your object angular size becomes smaller and smaller, the background star.
So the blue line is meant to be the size of your star.
Right. Projected at the distance. Yeah. Yeah, so as I mentioned, the occultation event is essentially limited by the Fresnel scale, which is a function of wavelength and distance. For the main targets that we'll look at 43 AU, the Fresnel scale is 1.5 kilometer. And then the event width is roughly a factor of the Fresnel scale is around 5 kilometers. So any object that's essentially smaller than your Fresnel scale, you are limited by this event width. And then we mostly will observe our objects at our position, meaning the relative motion is highest with a velocity of 25 kilometers per second. So the event will span for 0.2 second. So this is a diffraction pattern assuming a perfect alignment, and then you have circular TNOs blocking the signal. So if we consider different possible cases, we can derive their light curve at 20 Hertz, which is the frequency that TAOS II will observe. Then you will have a feeling of how this signal change with different distance and also the different size of the objects. So here are two cases. One is that you observe at opposition, so meaning you have the highest relative velocity. But we can also choose to observe at the opposition angle of 60. In that case, the duration will be longer, then it's easier that you can catch the event. But because the object moves slower, So the coverage, the effective coverage of your field also becomes smaller. And this is a comparison of, like for example, this is 1 kilometer and this is 30 kilometers. So this is what I just mentioned. When you have a big object, then you basically do not see much of the diffraction effect, especially when you are at opposition. It goes very quickly. But if you are further away from opposition, you might be able to catch the diffraction pattern at the edge. And for object that's further away, you will start to see the effects of the background star, the angular size of a background star. So if you have a fainter object, then you can still see the diffraction pattern. But if the background star is brighter, meaning its angular size is bigger, then you probably won't see too much of a diffraction effect because the KBO, the angular size of a KBO is much smaller. And this is a perfect case, meaning that everything is circular. And then you observe through the center of the diffraction pattern. But in reality, we know that it's very hard that you have a circular object with a size of few kilometers or smaller, and also the event will not necessarily go through your telescope at the center. So in most cases, during your observation, you probably will see a quite different light curve, because the observation might pass through different region of this diffraction shadow. So here we plot the perfect case. These are the circular object that I mentioned, but we also try to simulate when the object is like a contact binary with different sizes. Then you will see that the light curve will become quite different. So in our real data, by the end, you will see a lot of this kind of events, which sometimes can tell you what's a real size, but sometimes you probably cannot tell you what's a real size of an object if it's quite elongated. So a little bit of history that actually we have run TAOS I based on the same idea back from 2005 to 2012. So we run 4 50-centimeter telescope. At that time, we monitor about 1,000 stars at 5 Hertz simultaneously. So collected about more than 1 million star hours data. And back then we use we call it a zipper mode operation. So we basically squeeze or stack the whole full frame image into a stripe. The drawback is that you will have all these strips that coming from the readout of the CCDs. So it generates additional noise in our light curve. But anyway, by the end we didn't detect any events which has enough significance in our statistics. So TAOS I basically set the upper limit of the possible size distribution back then. So when we start the TAOS II, we hope we can have a factor of 100 improvement in sensitivity over the first generation of TAOS. So this project has been a collaboration with UNAM in Mexico, CFA, Central University, and also the CADC. So we know that the telescope is hosted by our partner in UNAM in San Pedro Mártir Observatory, and CFA has been our long-term collaborator through Charles Alcock They provide technical advice for the telescope and in the beginning of the development of the camera. We're students from Central University, and CADC is taking care of the data archival of the TAOS II. Okay, so for TAOS II system, we hope to follow, roughly speaking, 3,000 to 10,000 stars simultaneously, in average in the order of 5,000 stars or more, because the event rate that we derive from the TAOS I result showing that you do need a lot of stars in order to get the events. So we have 1.3 meter telescope with a field view of 1.7 degrees. The limiting magnitude of 20 Hertz is so here we say 17.5, but recently we found it's probably a little bit less due to the seeing and all other effects I'll explain a bit later. We'll run it at 20 Hertz to well sample the light curve or the diffraction pattern that I mentioned. So we use CMOS imagers with a sub-aperture readout for 20 Hertz. And the three telescopes are separated by at least 100 meters to minimize the false positives from the scintillation. So this is the site, some statistics. In average, they said it's roughly speaking 300 nights per year. That's clear. So compared with what we had in Lulin, roughly speaking, is 100 nights or so. The site is very dark. It's in the middle of the peninsula, the Baja California, and then the seeing statistics. This was done by the TNT site survey. It shows a median seeing maybe around 0.7 arcsecond. So the picture shows the dome and then the three telescopes. So the furthest two telescopes are separated by 320 meters. The closest two is roughly speaking 120. This is the telescope. So we have three telescopes from the DFM engineering in Colorado. It's a modified RC design with a Schmidt corrector plate. The spec is that it should be, the image quality should have 80% of enclosed energy within 0.8 arcsecond on axis and 1 arcsecond at the edge of the field. And then the checking error should be smaller than 1 arcsecond with an open loop. This is a camera. We developed with ETV for a custom device. It's a 16 micron pixel, correspond to 0.63 arcsecond with a telescope. Each of them is roughly speaking 2K by 4.5K. It's 3-side bountable, so 10 of them can cover our effective field view. So this is our field view. In order to avoid the huge amount of data, so as I mentioned, we will have sub-aperture readout. We can assess or program the sensor so we can read out any small regions that we need to sample in our field view. These are the picture of the cameras. So 10 of them, they are aligned within 20 to 30 microns to stay at the focal plane. We develop the mechanical structure and as well as readout circuits. Each sensor has FPGA electronics to read it out. So this shows the characteristics of the camera. The full well of a camera is smaller than the typical CCD, around 16,000 electrons. The noise is between 2 and 3 electrons. These are the real measured noise from our delivery camera. So the data sets, later I'll show all the fields, but roughly speaking, we'll have around 30 major target fields that we will observe depending on the year, the time of the year. I will stay on the same field for 2 to 3 hours. So roughly speaking, we will monitor the photometry of 200,000 stars at 20 Hertz with 3 to 5 years. And we use a wideband filter from 350 to 720 nanometers so that we can get more light to go to a deeper sensitivity. And we will also have field acquisition and focus images. So these can be stacked into deep images as time goes by, and it probably can also be used for variable and transient studies. So these are the candidate fields, and we have generated a catalog of all the stars within all these small boxes, and we understand that by the end they will trim down all these fields and use, roughly speaking, 30 of them for our survey.
So for the total naive for this guy.
Mhm.
So this is ecliptic coordinates, and what is that?
So this is a ecliptic plane.
The ecliptic plane.
Yeah. So because this is a location where most of TNOs are. So in the beginning of our survey, we'll focus on these fields, and then as we accumulate more events, we'll start to move away from the plane so that we can know the inclination distribution.
And you're always looking away from the sun, or what? Do you have an LST range that you look at?
So basically, every night we will observe the field that's near the opposition.
Opposition.
Yeah, so that the relative velocity is the highest to increase sky coverage. Okay. So for TAOS II, because it's a little bit different from TAOS I because of a higher sampling of the light curve. In TAOS I, we only have 5 Hertz light curve, so meaning every event is just one dip. But for TAOS II, every event we will be able to sample the event width and also the depth. So we are trying to generate a database, a light curve database with synthetic light curves, so that we can compare the observed data with the database to extract the possible event parameters. So this has been models that we generated, as I mentioned, from the light curve data we generated. So here you can see we define equivalent width and equivalent depth of the occultation events. And with these 2 parameters, we hope that we can quickly sort of converge to where is a real possible event parameters. So this has been generated, and we are now currently running try to develop a survey simulator, utilize this, and integrate with the survey strategy, and try to by the end generate a event survey efficiency with different kinds of TNO size. So here's the very rough survey sensitivity that we derive. So here we try to use the parameter listed here 5 years and 300 nights with 5,000 stars. So we can get in total 60 million star hours of data, and you can put into the calculation and calculate what's effective coverage of a survey. So compared with TAOS I, of course, we can see this is a huge jump. And here you can see, roughly speaking, 100 times of improvement. But here we have two estimations. One is optimistic estimation, and then the dash line shows a more conserved plot. Because when you get to a smaller object, the signal to noise ratio of your light curve actually is a key to determine how effective you can detect these objects. But in any case, we expect a huge improvement of the number density that we can detect with TAOS II. So here what we show here are all the measurements or all the models that I showed earlier, converted to the number density of objects, and then this is a detection limit of a TAOS II survey. So meaning no matter which models by the end is the correct one, TAOS II will be able to detect it. And this product is a very similar product, but we picked the two. So this is a model, as we mentioned, they use the crater model, and then this is another model. They use their results from the Hubble Space Telescope guided data, and we can derive what's a possible event rate. So basically, we should be able to get to about 100 events through our survey. So this is one of the example of the window data that we collected last year. So basically, you just let the camera run at 20 hertz. You can see a movie like this.
What is this? Is this the same star? Or
What?
are these 30 different stars, or is it the same star?
No, they are different stars in our fields.
And that's real time. Like this is 1 second per second?
This is 20 hertz movie. Yeah, but this only lasts for maybe 5 weeks. Yeah, I only put like maybe 10 seconds.
And what's the pixel size?
Pixel size is, as I mentioned, 0.6 arcsecond.
What you're seeing?
So the seeing was taken during not very good seeing. So it's seeing between 2 and 1.5 arcsecond.
I said your median is 0.7. Why do you call 2 to be good?
No, I didn't call 2 is good. I said this is the data took under 2 arcsecond seeing.
Okay.
Yeah. So we use observation to generate a light curve. So this is a light curve of the stars that you saw in this data.
Did you guide during the observations?
Not yet. Yeah, we will guide. Yeah, but right now, this data we didn't. Yeah, reason why I show this data is just to show something that we did not expect. So apparently, you see a big fluctuation of the flux of the stars.
Foreseen data.
Yeah, it's like 2 arcseconds. Yeah. So you see all the stars. These are bright stars at different corner of the cameras, but they basically shows the same effects. So we can try to generate a medium of these light curves, and then subtract the trend, then you can get the beta light curve as shown here. So this is
These 5 stars
yeah, these are 5 different stars.
nearby.
No, they are different in our field, of course.
So they have some systematic fluctuation.
Yeah, from the sky.
No. If it's from different corner, how come they will sort of synchronize?
Yeah, because the sky is doing that.
Because of turbulence of the sky.
Yeah, because it's under very not so good seeing.
So what's the resolution of
20 hertz.
So like what's okay, there's a second. So it's like a
1 minute.
1 second fluctuation.
This is 1 minute.
Oh, yeah, okay.
Yeah,
So the
and
fluctuation is like
each point is 20 hertz.
okay.
Yeah. And also, actually, you can also measure how the star is moving around with the seeing. This shows the x and y coordinate of the centroid of the stars. So at 20 hertz, you can see how the seeing affects you. If the seeing is really bad, this is just a warning to us. We need to take some care of our data.
This can be problematic when seeing is good, because then your pixel will be undersampled in the scene.
Right, will be slightly under sample, but our optical quality is 0.8. So combine the two is probably it's slightly under sample, yes.
It's undersampled, and if seeing move your star around.
Yeah, but we are not asking for the 1% photometry accuracy. Yeah, we know in the beginning. It's very hard if you want to have well sampled point spreading function and then coverage of Y field and 20 hertz. They are just straight up there. Okay, so current status. So we have 3 telescopes right now. 2 of them, they are running smoothly, can operate remotely. This is in December that we just run it here. In the afternoon, it's 9 in Mexico. It's very nice. You can run it. And it was one of the images we took for KG and UEG. They want to play with MM31 for pixel lensing. We have some trouble with side 1. The camera temperature controller was burned during one of the lightning strike. It's still under repairing. It should be back pretty soon. The image quality for side 1 needs some improvement. So we now know what's the problem. We will soon make we're making a mask to match the very age of our mirrors. I expect to solve this issue. So what should we do before we start a survey? The first thing is I mentioned the confirmation of side 1. In terms of control software, we'll just need to put everything together, and the window mode. Right now, as I show the window mode data, we need to type and select the stars. We are now integrate the whole process together. So once you collect a full frame image, you can select automatically detect the star and then select your windows. And then the field selector is just like a scheduling software. We need to adapt it from what we did in TAOS I to TAOS II system, and also, the camera control code, just to integrate every small pieces. Now, some imaging processing we need to do, including automatic bias flat correction. And then once we start to collect the data, we will have to optimize the photometry So we have several ways to do the photometry. The quick dirty one is that we just sum up all the pixel value in our small window, and then later we can do like, point splitting function fitting or circular photometry, aperture photometry to compare what's best for it. And our colleagues in UNAM and CADC, they are also working together to try to mirror our data, and eventually we can have a searchable mechanism in CADC, so we can query any data we want effectively. So I think right now our goal is to start the normal operation pretty soon, in April or May. So meanwhile, we are organizing this TAOS II science workshop in UNAM in Ensenada. This is a website. I'll soon post it in our institute website. The idea is to provide the menu to discuss possible science other than the TAOS II TNO science, because as I mentioned, there are huge amount of light curves that you can use for like variable stars, exoplanet, or some other transient events. And we hope that among the partners from Taiwan, from UNAM, from CFA or CADC, we can all jointly working on the other sciences. And this workshop will also provide a chance for people to think about what to do after the survey. The survey will be done in 3 to 5 years, and the telescope will still be there. You can use for other things. So I already identified some certain people to attend the workshop, but if you are interested in attending, please let me know, because we also have a site visit, so it's a limit amount of people that can attend for the event. Okay, so in summary, we look forward to the full operation in the next couple of months. Should be able to detect more than 10 events in this year. Then we'll have a huge data coming up. So please think about what you can do with our data. That's it.
Thank you very much.
Any questions? Comments?
Yes, I'm not sure I understood your answer to Ming Tang's question, which is, what do you learn if once you find 10 events?
Well, 10 events is probably not enough. We do need 100 events to plot.
100 events.
Then we can rule out the models or identify which model is closest to the site situation we extract.
What my takeaway was that they're models anyway. I mean, it doesn't matter what you measure, there'll be some model that's consistent and some model that's not. We already know that. So you said the models have, unknown physics, unknown parameters, very little is known. So okay, so I have an infinite space of parameters, and now I have a smaller but still infinite space of parameters. So I guess Ming Tang was really asking, okay, so previously it's infinite, now it's still infinite but much smaller. And
this is the same for all science projects, right?
Well, no, I think you for example, if somebody were to ask him, not that I know nothing about transformation, but maybe there are many more experts in the room. But for example, people will ask, what's the coagulation, or what's the resonance fragmentation of this? So I don't know what the question people ask. Does this relate to any other person, any other field's questions about planet formation?
Yeah. So for example, there have been argument of how the star or planet can form from dust to be the paper pile and then grow up. And I think this is one of the pieces that they need to understand.
For example, something concrete. So, I'm clearly the wrong person to be asking the question, as I know nothing about planet formation. But at the end of the day, in the planet formation, my understanding is that to get a picture, there are certain questions like how do you form, from dust you get centimeter-sized objects. Supposedly that's hard. And then you go from where are the experts here? Then you form, bigger. You want to look at kilometer-sized objects. So, what kind of measurement would tell you what about this process? Like what, what, I don't know. But, so I really don't know what people are looking for or asking, but I'm really the wrong person to ask. But I was asking, how does this connect to some other researchers' question about planet formation? What will they know that they didn't know before? Or maybe some other planet researchers should answer.
I'll point out that there are different formation mechanisms in some of those different models. And I'll also point out that there hasn't been much work done on it in the past 10 years because there's no way to test any of these theories. So one thing I would expect is that there would be a lot more work that would start coming out from the theorists and stuff. If that helps answer your question. But I mean, the last model that was on there was from 2013. And the 2019 model on there was not a model. That was it's sort of a model. It's a model of converting crater sizes to TNO sizes.
Maybe even the bigger picture here is that, okay, so my total ignorance, I know nothing about planet formation, is that you start off with small things and try to make big things. That's not the basic picture of, and the challenge is how do you make something the size of a kilometer even, or the size of the Earth or the Jupiter. You've got to somehow get things to get bigger. So that was the number one challenge. Now, and that I thought is not fully solved yet. Now, you're saying these objects, in your picture, you're saying are dominated by the other process of making big objects smaller. So you've got first to get up, and then you've got to get back and make them smaller again. I think that's what I thought that your picture at least was of how these objects come about. Meaning you first have to get them big, then you've got to make them small again. You said there's uncertainty.
No, there's a balance between the two, right? You things getting bigger, and also the collision make it smaller. So that's why this size distribution is important, because you can understand what are the dominating mechanism in this process. Because it's not like you grow and then you break down. The two things happen at the same time. Yeah.
Well, I think this is, I'm not sure, I don't think that is clear. And I think the way this point, I would maybe ask whether these objects can be a source, a new source of forming planets, or can they be a reservoir of forming new planets? I think that would be something new, because generally if you talk about this star, this planet formation, that's not what that community thinks. So we think that is streamers, accretion, when you form this out of gas, primordial gas in that sense. So this is different. If you think that there's a balance between that building up and destroying, then the question would be whether this is a source of material that can lead to maybe new planets. And that could be linked to all the groups. Or whether this is common in other cases.
And there's also the question when you try to form planets from dust and gas. There's many barriers to build up the planetesimals. And these objects, the small objects that we haven't observed in TNOs, are all the same size of the planetesimals that we expect are the building blocks of the planets, which is kind of odd that we can only, well, there's a small number of big objects, but there's a lot of them that we're missing just because we're not able to see them. So I think in looking at these smaller objects will tell us what sizes we can put in our simulations to kind of make or break the barrier of building planets, at least in simulations.
So I have another question. So you were showing this lightcurve, so these dips and this pattern. So I assume that is always only for one TNO, I guess.
For one, yeah.
So is there a chance that actually if these objects are very small, and for example, if they occur because there was an impact, then for at least for some time they are still nearby, they're not too far in distance.
The binaries?
There is multiple objects that you would observe. There's
Uh,
an overlap, and so that would be very different, or maybe that would be even a window that could be a window to see more of even smaller objects.
That'd be really hard.
Yeah.
Hard to see.
well, the fraction of
There's one collisional family known, and they're already very, very far apart.
So I guess typically you wouldn't see that because the star is far away and you're not that close.
Yeah.
Right.
It would have to be within, well, within a kilometer.
yeah, the binary fraction is the 10 to 20% for TNOs that we know, and some of them they're actually not close. They're quite
The
separate.
reduction of your background stars is more than 50%. So 1% of the time you will see the same guy crossing both stars, don't you?
We in our catalog will try to mark if they are known binary stars, so that we know that dealing with light curves we have to be more careful. But of course, if there are some unknown binary stars, we might see something in a light curve.
Well, I mean, that's good, right? Because you
Yeah.
find velocity out back because you get double lensing, double occultation 1% of the time, roughly speaking, because typically AU separation solar mass star is about 1% of the, no.
Yeah, there was in TAOS one. In TAOS one, there was a occultation, known X-ray occultation through a binary stars, and you can see, you can see the feature, like a cold one and then the other one. Yeah. So if there's unknown binary stars and happen to have events, then we should be able to tell.
With unknown, you just get two events,
Yeah.
and then you go back later. These are white stars. You'll figure out what the binary properties are. Next month by looking at.
Yeah.
Well, in my simple mind, now you have a orbit, a whole bunch of large TNOs circling around it in a random motion. They bump into each other, destroy each other, become smaller objects. Then eventually, as time goes on, they become smaller, 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 and smaller.
No, not necessarily like that.
Well,
Because if you look at this object,
Will that eventually will gel again and will become bigger?
We expect most of the erosion took place during the migration of Neptune. Things got stirred up, and then
so this object
became more stable now.
is a result of two objects combining together.
By accident.
Oh yeah, purely chance.
Yes.
Yeah.
So it's an outlier. Could it be just outlier? Or could it be no?
Oh, that's why.
In a random process, you always can get something that's out of ordinary. But in a statistical sense, is this a
Statistically, this is not rare.
law or a process?
There has
physical
been
process
there
or
has
is-
been
Statistically, 100% of the directly observed TNOs are compact binaries, because that is 100% of the.
but there's a group. They've been trying to use occultation technology to understand the shape. So Mark Bowie has been running this, and I remember that when I see this weird shape, I think the fraction is high. It's not low.
How big is this?
This is 20 to 30 kilometers. Yeah.
And it's orbiting Pluto.
No, only the sun.
This was found by New Horizons after it passed Pluto.
By chance?
No.
No, there's an original target.
Went
They
and did a flyby.
yeah.
Intentionally.
Yeah, they fly by Pluto and then found another target. That's this one. They only fly by.
But there were already predictions of the shape, so it was a good confirmation that the occultation works for
Yeah.
seeing shapes.
Just light curve measurements show that a lot of the TNOs are compact binaries.
Compact binaries or peanuts like this.
Well, that's sort of compact binaries. When you get that small, they're not. It's got a
Compact binary.
Sorry.
Contact binaries.
Well, I will be interested in this rotation direction. Because the formation, if you just like, say, just do by doing collapse, no matter what that is, like any kind of instability,
Mm-hmm.
and if they have this, like appropriate retrograde, if this collision, it can be random. So, but I guess, in terms of even 20 hertz, you cannot detect the variation.
Yeah, we cannot. We don't have the orbit information.
Right.
Yeah.
Not orbit, but just space.
No. Yeah. We can only
Right, the snapshot.
take the snapshot.
We should be sensitive to objects large enough that we can follow up with JWST, and we're already planning on proposing for that. So if we do find a large enough one, we should be able to, we can follow it up within a couple days. We should be able to see it.
Good. Any other final comments, questions?
There was a question.
Jim Fabrice.
What is the smallest object that GWS can map?
There's currently a project ongoing. I think they are talking about like 15 kilometers.
15.
Yeah.
Good. So let's thank Shiang-Yu again.
Okay.